Hello, my wonderful AP class. I miss you guys. I've said this 800 times, but I really do miss you guys. As we get closer to June, it reminds me how much I really do miss you guys and how long it has been. This is week 9 of classes, week 10 away from you guys. So that's 2.5 months, which is unbearably long and really sucky. But highlight. We have this lesson, which is area between graphs and between curves. And I might break it into 2 podcasts. We'll see how long it goes. But that's the lesson for this week. It's just area between graphs, graphs that are y equals graphs and graphs that are x equals graphs. And then the next 2 weeks after that is volumes of revolution. And I'm giving you guys 2 weeks to work on it. And like I said, Khan Academy, where you're going to find those ones. So you guys can get prepped for university as to where you guys can look if you ever need help. And then your last week is a year-long review. And the year-long review is like your final, but an assignment. So the very last week is just a review assignment from the very beginning of the year till now. So yeah. So you really only have 2 new lessons left. Area between curves or graphs and volumes of revolution. So let's get this one started. So in a function, f is continuous and non-negative on a closed interval ab, the definite integral between ab f of x d of x equals the area under the curve of y equals f of x from a to b. So if you were just trying to find the area under the curve, which we found already, all you did was you found the integral between those 2 x values, which meant that you found the antiderivative of it, plugged in the values. In this section, we relax the restriction that f of x is non-negative and extend the interpretation of the definite integral to find the area enclosed by the graphs of 2 functions, not just one between x values, but 2. So finding the area between the graphs of 2 functions by partitioning the x-axis. Suppose we want to find the area A of a region enclosed by the graphs of y equals f of x and g of x and the lines x equals a and x equals b. So you say you have a graph below and a graph above, and you're trying to find the area between those graphs between 2 x values. Okay? Occasionally, the area can be found using geometry. Oh my goodness, guys. Geometry formulas for specific shapes. So if it was like you could fit exact triangles and rectangles into the shape, and they do this in physics, then you could find actually areas of the triangles and areas of the rectangles and areas of the half circles. And you could just use geometry and add up all those different areas. And that'd be fine. But, and then calculus would not be needed. But more often, the region is irregular. You can't just fit in triangles and squares and semicircles and circles. And its area is found using definite integrals. So we're in calculus. So even if you could just use shapes, we wouldn't be doing that. We would be finding the definite integral between the 2. So, area. The area of the region enclosed, I can't read today, guys, by the graphs of y equals f of x and y equals g of x, and the line x equals a and x equals b, where f and g are continuous intervals between a, b. So it means there's no breaks in them. It's not if it was a rational graph, it would have to be on the continuous part. You wouldn't be able to have an asymptote portion. So you could find the area between a curve with a rational function, but it would have to be on a continuous part of the rational function. And f of x is greater than or equal to g of x. So that means that f of x, the graph, is above the g of x graph. Okay, it has to be higher. Then all you do is you find between a and b, and you take the f of x function, the one that's the highest or furthest above the x-axis, and you subtract off the g of x function. So there's one extra step involved when you have 2 equations now. You actually have to take the higher function and subtract the lower function, and then you can find the integral. So there's just that extra step. So example 1, finding the area between the graph of 2 functions. Find the area A of the region enclosed by the graphs of f of x equals ex, e to the power of x, and g of x equals square root x, and the lines x equals 0 and x equals 1. So the x equals 0 and x equals 1 portion get a little highlighter out here. Sure, pink. X equals 0 and x equals 1. That's your A and your B values. So the lower one's the one to the left is your A and the one to the right is your B. So A is 0 and B is 1. And then we have graphs. F of x equals e to the x and g of x equals square root x. Now that doesn't mean those are the f of x and g of x in this equation in particular. It just means that there are two different functions that graph differently. So what do we need to know? Well, we need to know what graph is higher or further away or further above the x-axis. Because once we find that, the rest we all know how to do. The rest is just integration, and we've done that over and over and over. So step 1 then will always be to graph the functions to determine which function has larger y values. Right? And then that's one that's f(x). Larger y values means further away from the x-axis, above the x-axis. Okay? So the first thing we're going to do is sketch these two graphs. So let's do f of x. I'm going to just zoom in here because it's easier for me to write. F of x equals e to the x. Okay? So I'm going to do myself a little table of values to help myself out. X and y. And I'm going up by, because it's between 0 and 1, I'm going to go 0, 0.25. Because if I just did 0 and 1, I'd have 2 points. Right? And I want to have a few points to sketch. 0.5, 0.75, and 1. Now, I can plug 0 in for the x of this equation, and I get e to the 0. And e to the 0 is 1, so that's my 1 point. Then I go e to the power of 0.25, and that rounds to 1.28. And then I go e to the power of 0.5, and I get rounded to nearest hundredth, 1.65. And then I go e to the 0.75, and I get rounded 2.12. And then I get e to the 1, which is 2.72 rounded. Okay? So that's for my e to the x graph, and I'll sketch that in a second. Let's do Christmas. Why not? We're in weird times. Let's do some Christmas because Christmas makes me happy. So x, y, and we do g of x equals square root x. So I'm still going to do the same one. 0, 0.25. That does not look like 5. That's a little better. 0.5, 0.75, and 1. So if I put 0 in for the x, I get square root of 0, which is 0. If I put 0 in 0.25 in for x, I get the square root of 0.25, which rounds to 0.5. 0.5 in, get the square root of 0.5, which is 0.71. And then I put 0.75 in for x, and I get the rounded version of 0.87. And the square root of 1 is 1, sorry. All right, now I'm going to sketch it. What I did to sketch it is I picked a straight line here. Holy moly, that was free-handed. Is anyone else impressed? I'm super impressed. Look how straight that was. I'm never going to do that vertically. I can only do straight lines horizontally. Let's see. And then I'm going to do one here. Well, it wasn't horrific, but it wasn't that great. Now I have to put my scales are. So I'm going to make my x scale be 0.25. So that means each tick is worth 0.25. So it's not going to take up very much of the graph. You can make them, so this would be 0.5. This would be 1. So you could take up way more. 2, 3, 4. Yeah. And I'm going to make my y scale. They don't have to be the same, but I'm going to make them the same. So I'm going to make my y scale be 0.5 actually. So this would be 1, 2, 3, 4, 5, 6, -1. Okay, so I'm going to sketch the red one first, which is the e to the x graph. So I have 0 and 1. This is where the sketching is going to get bad. 0.25 and 1.28. 0.5 and 1.65. 0.75 and 2.12. And 1 and 2.72. And the graph would keep going, right? Technically, it would keep going this way and this way. But I don't care about the rest of the graph because I want it between x equals 0 and x equals 1. That's where I'm looking. Okay, I need to plot my green graph between those values. 0, 0, 0.25 and 0.5, 0.5 and 0.71, 0.87, and 1 and 1. So it looks something like this. Imagine that's drawn nicely. Okay, now what we're trying to find is the area between these curves. Okay? And the rule that I gave is that, sorry, my phone is buzzing here. My child's deciding to message me, and she's in the room beside me. Okay, so our rule is that we have to find the higher up graph and subtract the lower graph from it. So the higher graph is the e to the x graph. It's the red graph. And the lower graph is the square root x graph. So it says here, graph it. Step 2, write out the definite integral equation making f of x and g of x and a, b values. So we know that f of x is e to the x, and it's greater than or equal to square root x. So we know that this is going to be my f of x, this is going to be my g of x in the formula. My a is the lower bound, so a equals 0, because x equals 0, to x equals 1, so my b is 1. So when I go to sketch out my definite integral, sorry, not indefinite, I know it's defined between 0 and 1. I take my higher up equation, which is e to the x. I subtract my lower equation, which is square root x. And I find the integral between that. That's it. That's the hardest part. Is finding out which one's the higher one. Okay. So now I'm going to rewrite it because I always told you to rewrite square roots as to the power of a half, which is important. So I'm going to go e to the x minus x to the half dx. All right. Wouldn't be me if I didn't put random black lines on pages. Okay. So now we do the antiderivative of e to the x, which is awesome because it's just e to the x. The antiderivative of minus x to the half, I add 1 to it. So a half plus 1 is 3 over 2. Then I'm going to divide by 3 over 2 or multiply by 2 over 3. Because remember, it always flips as your coefficient. And then I get a plus c from 0 to 1. So it's not much different than what we did. The hardest part is figuring out which graph is above. Okay? And then we fill it in. So we're going to get e to the 1 minus 2/3 1 to the 3/2 plus c minus e to the 0 minus 2/3 0 to the 3/2 plus c. Which gets me e to the 1 is e, negative 2/3, these c's are going to cancel, negative 2/3 times 1 is negative 2/3, and e to the 0 is actually minus 1. And then we'd get minus 0, so we don't put it, and the c's cancel. And you put negative 2/3 minus 1, that's negative 2/3 minus 3/3, so you get e minus 5/3, and it's an area, so it's in square units. That's the answer. That's the area between the two. And you could turn that into a decimal. And remember, you can plug this integral into your calculator. The only problem is if you put the wrong one. So that's why graphing it is so important, to check and see which one's higher. Could you put them in your calculator and check? Absolutely. Do they give you a calculator in university? Not so much. So I always try and teach you guys how to do it if your calculator is not available. So that's why I made the t-tables. Okay? So if you typed your definite integral into your calculator, you would get the same answer, and then you know you didn't make a mistake. So always good to check. All right, page 2. A little bit different. Always do a little bit different each time. So the last one I gave you 2 equations and which x values between it would fall, right? This one's a little different. This one says, finding the area between the graphs of 2 functions, find the area A of the regions enclosed by the graph 10x minus x squared and 3x minus 8. So, they didn't give us the x values. It didn't say between x equals 0 and x equals 1. So it wants the region that they're enclosed by. So what we need to do actually is sketch them first. That's the very first thing we're going to need to do. And then we're going to need to find out where they intersect, because that is going to give us our 2 x values. That will give us our A and our B for the equation. Okay, so the last one was a bit easier because I gave you the A and the B. I told you which x values it had to be bounded by. But in this case, it doesn't give you which x values it has to be bounded by. It just gives you the 2 graphs, which you'll have to draw, and then find out what it's bounded by. Okay, so let's sketch these out. So we have y equals, I want to do it in a color. Let's do dark blue. And zoom in. So we get y equals 10x minus x squared. And I want to sketch that. And to be honest, because I don't want to over sketch, I don't want to do too much, I'm actually going to cheat and I'm going to go to step 2 and find out where they intersect. Because if I find out the 2 x values where they intersect, I know I can just sketch the graph between those. How do I find out where they intersect? You literally set the equations equal to each other. So I go 10x minus x squared equals 3x minus 8. And you did this in quadratic linear in 20-1. This is where you did it. Okay, so I'm going to move, it's a quadratic, so I'm going to move everything to one side. So I'm going to go add the x squared, subtract the 10x, add the x squared, subtract the 10x, and I'm going to get 10x. So I'm going to get x squared minus 7x minus 8, and then I'm going to what multiplies can be negative 8, and that's going to be negative 7, x minus 8, x plus 1. I don't have to do decomp because this particular equation has a 1, x squared. And then when I solve them out, I get x equals negative 1 and x equals 8. And this is my A, and this is my B. Why would I skip ahead? Because now I know if I draw the graphs between negative 1 and 8, I have both graphs for what I need to see. Right? Right. Okay. So I kind of cheated and found out I needed negative 1 and 8. So I'm going to go x, y, negative 1, and then 0, 1, 2, 3, 4, 5, 6, 7, 8. You can probably hear Isla because she's not quiet. I apologize. Okay, and we plug the negative 1 in for my x's. It's an x. So I'm going to get 10 times negative 1 minus negative 1 squared. I'm going to get negative 11. When I plug the 0 in, I get 0. When I plug the 1 in, I get 9. When I plug the 2 in, I get 16. When I plug the 3 in, I get 21. When I plug the 4 in, I get 24. When I plug the 5 in, I get 25. When I plug the 6 in, I get 24. What the heck? It's going back down. Oh, right. My graph is a quadratic. So it's going to be a parabola. 7 in, I get 21. 8 in, I get 16. Then my other equation is y equals 3x minus 8. It's a linear graph. So I need between x and y, between the x values of negative 1 and 8. Negative 1, 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, when I plug negative 1 into here, I get negative 11. See, they match. So they intersect there. 0, I get negative 8. 1, I get negative 5. 2, I get negative 2. 3, I get 1. 4, I get 4. 5, I get 7. 6, I get 10. 7, I get 13. And 8, I get 16. Okay. Then what I did is I went, I'm going to grab the black pen again. I went up 4 from the bottom, and I made my x-axis, which once again, that was actually pretty impressive. It started off rough, but it went well. And then I went over. Oh no, I'm trying to draw it vertically. Okay. I made my x-axis, my x scale, B1, and my y scale, B4. All right. So go plot those. Okay. So I'm going to go negative. Oh, wait. I made the x scale before. So I'm going to make this before 8, 10, 12, 16, 24. And then I get 28, 32, and then 40. And then I get negative 8 and negative 16. And then these are all 1. So I'm just going to go 2, 4, 6, 8, 10, 12, and then negative 2. All right. So we have negative 1 and negative 11. So that's about here. I'm plotting the x-squared one, which I should be plotting in blue. Silly me. Okay, so I have negative 1 and negative 11. And then I have 0, 0. And then I have 1, 9. And then I have 2, 16. And then I have 3, 21. And then I have 4 and 24. And then I have 5 and 25. And then 6 and 24. 7 and 21. 8 and 16. And then I'll show you why I don't sketch more. You'll see in a second when I go to sketch the other one. Okay, so that's the blue one. Oh no, I did them both in blue. Stunner. I am. Okay, so that's the first one. And then this one is going to be in pink. So negative 1 and negative 11, look, same spot. And then 0 and negative 8. Then 1 and negative 5. And then 2 and negative 2. 3 and 1. 4 and 4. 5 and 7. 6 and 10. Oh my goodness. Oh, this isn't 12, this is 16. Okay, 6 and 10, and then 7 and 13, and then 8 and 16. Oh, I drew those in the wrong spot. It was at 2 and 16, and here in 16, so it should have went like, oops, like that, and like that. There, now they actually touched. Okay, so that's where they would, this one would keep going, but we don't care about it. The blue one would keep going, but we don't care about it because we just want the area where they are enclosed. So that's why we have to find their intersections. So when you look at the area that they're enclosed by, It's this area here. And then when we do the integral symbol, we have to figure out which one is higher. Well, the one that's higher is actually the quadratic. So we know that we have 10x minus x squared is greater than 3x minus 8. And we know our a equals -1 and our b equals 8. And then I can do my integral. So my integral is, my integral is from -1 to 8. And it is 10x minus x squared minus the lower one, so 3x minus 8 dx. And if you sketch it, you can even find the intersections that way often too, right? But if they're decimal intersections, you really need to use your algebra to find them. All right. So then that gets us an integral from -1 to 8 of 10x minus x squared minus 3x plus 8 dx, which gets us an integral, if we combine like terms, so it's easier to do the antiderivative, of -x squared minus 3x plus 10x is plus 7x plus 8 dx. And then we can do the antiderivative of that. So we're going to get x squared is going to become x cubed, and we're going to divide by 3. So I'm going to get -1/3 x cubed plus 7/2 x squared plus 8x plus c from -1 to 8. And so that's going to give me -1/3 8 cubed plus 7/2 times 8 squared plus 8 times 8 plus c minus -1/3 1 cubed, cubed plus 7/2 times -1 squared plus 8 times -1 plus c. And so we're going to get -512/3 plus 224 plus 64, c's cancel, minus 1/3 minus 7/2 plus 8, which gets me 243 divided by 2, or 121.5 square units. Okay, so we did one where I asked for the area between two graphs from two specific x values, to one where I asked you for the area enclosed by two specific graphs, and you had to find the intersections to find their x values. And then we're going to go to example 3, which I'm just showing you, but I'm not giving you one like this in your homework, but I want you to be prepared for university with it. So it's find the area of the region enclosed by the graphs of y equals sine x and y equals cos x from the x-axis to their first point of intersection in the first quadrant. So in the first quadrant of your unit circle, right? So we have sine x and we have cos x. So down here I'm just going to go, when does sine x equals cos x? Because that's where we're really, the first time where sine x equals cos x. Because we're trying to find out where the two intersect. And when we do that, we set them equal to each other. Well, with this, we go to our unit circle, right? And where's the first time that sine x equals cos x? Right here. When it's root 2 over 2, comma root 2 over 2, right? That's when our sine x would actually equal our cos x. And what value is that at? Pi over 4. So they want it from the y-axis is when x equals 0. So between x equals 0 and x equals pi over 4. So that's all we're going to really need to sketch. So there's way more we could sketch, and it doesn't hurt if you do sketch more, but you don't have to. So we need to sketch y equals sine x and y equals cos x from 0 to pi over 4. So we have 0, we have pi over 6, pi over 4, and that's all we really need to go to. At 0, y is 0. At pi over 6, y is 0.5. And at pi over 4, it's root 2 over 2, which I turned into a decimal is 0.707. So 7.1. So I'll do this in black. So the sign is going to be 0. And then this would be pi over 6. This would be pi over 3. And then directly in the middle here is actually pi over 4, just like your unit circle. So we have 0, 0, and then this is 0.5, and this is 1. Okay, so we have pi, 0, 0, pi over 6 and 0.5, and pi over 4 and 0.707. So somewhere in there. And so it's going to go like that. And that's my sine graph. My cos graph, I'm going to do in red, so it sticks out. So you can see the difference. So we have x, we have y. 0 on the cos graph is 1. At pi over 6, we have root 3 over 2. So you're just pulling this off our unit circle, which is 0.8660 or something like that. And then pi over 4 is root 2 over 2, which is 0.707. So we're going to still plot that. So at 0, we have 1. And then we have, at pi over 6, we have 0.866 whatever. And then it goes to here. So we're doing this. And we're trying to find the area in between. This area in here. So which is my higher graph? The cos graph, the red graph. So when I go, I'm going to say cos x is greater than or equal to sine x. My a is 0. My b is pi over 4. My b is always my further one. And then I can do my integral, my definite integral. So I'm going to go from 0 to pi over 4, my highest, which is cos x, minus my lowest, which is sine x, dx. Then I do the antiderivative of that. So the antiderivative of cos is sine, because the derivative of sine is cos. So the antiderivative of cos is sine x. The antiderivative of negative sine x is positive cos x. Right? Because the derivative of cos x or anything with a c is actually negative. And then plus c from 0 to pi over 4. So I'm going to get sine of pi over 4 plus cos of pi over 4 plus c minus sine of 0 plus cos of 0 plus c. Now sine of pi over 4 is root 2 over 2. Cos of pi over 4 is root 2 over 2. The c's are going to cancel. Minus sine of 0 is 0. Minus cos of 0 is 1. And it's minus because we have to remember to distribute the minus sign in. So we're technically going to get root 2 over 2 plus root 2 over 2 is 2 root 2 over 2 minus 1. The 2's in front can cancel. So my answer is actually root 2 minus 1 square meters. Okay. So we've went an area between two curves, and I give you specific x values to area between two curves, and I want the enclosed area, so you have to find the x values of intersection. to a trig one, because I wanted you to try a trig one out. Okay, then we get to the hardest one with the x-axis, and then we're going to do ones where we define the area between the curves to the y-axis. So that's going to be our last two. Okay, so here we have finding the area of a graph of the x and the x-axis. Find the area A of the region enclosed by the graph of x squared minus 4 and the x-axis. So that's actually two equations. You have to be able to spot that. When it says the x-axis, that means g of x, or the other equation, is just 0. Because the x-axis is y equals 0, right? So here, this is actually very similar to the very first question I gave you. You define between two equations and the x-axis. And then x equals 0 and x equals 5. So we still have to sketch these first, and you'll see why. So I went up 3, and I drew a line. And then I went over 2, and I drew a line. And I made my x scale be 0.5. And I made my y scale be 2. So this is negative 4. This is 4, 8, 12, 16, 18, 20. And then 0.5, so this is 1, 2, 3, 4, 5, 6, negative 1. Okay. So the x-axis is an easy line. This is the one line we're going between. So we're doing the line y equals 0. And then in blue, we'll do the line y equals, it's not the line, I guess the quadratic, x squared minus 4, the graph. And we need between 0 and 5. So I'm going to make this between 0 and 5. 0, 1, 2, 3, 4, 5. So I plug 0 in, I get negative 4. I plug 1 in, I get negative 3. I plug 2 in, and I get 0. I plug 3 in, and I get 5. I plug 4 in, and I get 12. I plug 5 in, and I get 21. So I'm going to plot this one. 0 and negative 4. 1 and negative 3. 2 and 0. 3 and 5. 4 and 12. That's not very good. Pretend that's on the 12. And 5 and 21. And we want the area shaded between the two. Now this is where it's going to be different. Okay, this is one area shaded between the two. But look, it changes. And you will get something like this. And then this is to 5. So this is the other area. What's the change? We have two separate areas. And the change here is area 1, put it in black, area 1, y equals line, y equals 0 is actually the higher line. And area 2, the y equals x squared minus 4 is actually higher. So I'm going to have to do two integrals, and they shift at 2. So from 0 to 2, my y equals 0 line is higher up than my y equals x squared minus 4. And then from 2 to 5, my y equals x squared minus 4 is actually greater than my y equals 0. So I'm going to have two separate integrals here. This is my a and my b, with this being my 0 minus that. And then this is my a and my b with x squared minus 4 minus 0. So we have to do two separate integrals. This kind of goes in here. Okay, they intersect at 2. That's where the switch happens. So sketching these is so much more important because it just makes more sense. If you sketch them, you can see it. So area 1 is going to be the integral from 0 to 2. And then my y equals 0 is going to be my f of x graph. And then a minus my g of x, which is the lower one, x squared minus 4, because that's the lower one, dx. So the lower the y values, the one with the lower y values comes second, right? And then I'm going to have to add it to my area 2, which in this case now, my area 2, if you look at it, the blue is the higher to the red. So I'm going to have to go from 2 to 5 with actually x squared minus 4 first. Subtract 0 dx. So I'm doing two separate integrals. So here I'm going to get, technically you can put them together then. So I'm going to get 0 to 2, 0 minus x squared plus 4 dx, plus 2 to 5, x squared minus 4 minus 0 dx. So when I go to do the integral of it, the 0 doesn't matter. It's just gone, right? These zeros are gone, minusing 0. If you forget to go 0 minus the x squared minus 4, you're going to actually have the wrong signs because it becomes negative x squared plus 4, right? So now we do the integral of that. So x squared raised 1 is x cubed. So I'm going to get negative 1 divided by 3, x cubed, plus 4x plus c from 0 to 2, plus x squared, so you're going to get 1/3 x cubed minus 4x plus c from 2 to 5. And so then I'm going to have to do two longer fill-ins, right? So I'm going to get negative 1/3, 2 cubed, plus 4 times 2, plus c, minus negative 1/3, 0 cubed, plus 4 times 0, plus c, and then plus, do the next integral, 1/3 times 5 cubed, minus 4 times 5, plus c, minus 1/3, 2 cubed, minus 4 times 2, plus c. Now, you're going to have to do two areas every single time I give you a question where the two areas actually have an intersection between the x values. So if I ask you between x negative 1 and x7 and the graphs actually intersect in the middle and switch, you're always going to have to get two areas. Okay? So if we do the math for this, you're going to get, it's not letting me fill it in, negative, I don't know, if you type all this math in, give me the eraser. You're going to actually get equal to, no, switch pages, equal to, no, it's going to keep switching pages. I'm going to have to put it here. I don't have any room left. Sorry, guys. Not, oh, there. No, well, equal to 97/3 square units. So you guys can type it into your calculator and make sure you get that answer to practice doing your math. Okay, the one last type. So we went over different types of x's and all the different things I could throw at you. The last type is actually finding the area between the graphs of two functions by partitioning the y-axis. So in this case, and you're going to know it's one of these type of questions because the equation is going to be in x equals, not y equals. So The area A of the region enclosed by the graphs of x equals f of y and x equals g of y, and the horizontal lines y equals c and y equals d. So now they're y equals lines, not x equals lines, where f and g are continuous in the interval c of d. F of y is greater than or equal to g of y for all the y's in c of d. So basically you now need to just graph the graphs and find which graph has the largest x values, technically, which graph is the furthest right. Okay, so this one is find the area of the region enclosed by the graph x equals y plus 2 and x equals y squared. Now the easiest way to draw any graph is to get it into y equals. So we're going to always deal with them in x equals equations when we go to put them into our integrals or we go to integrate them. But to sketch the graph, I'm going to flip them into y equals because it makes my life so much easier. So I'm actually going to sketch this by moving the 2 over, and I'm going to sketch x minus 2. And for this one, I'm going to square root both sides. And when I take the square root, it's plus or minus. So I'm going to get y equals plus or minus square root x. So that's how I'm going to sketch them. But I only switch them into y equals just to sketch them. Other than that, they stay in x equals. So I made the x scale be 0.5 and the y scale be 0.5. So I made this one be going up by 0.5 and the y go up by 0.5. So this is 1, 2, 3. I'm going to scoop in 4, 5, 6, negative 1, negative 1, negative 2, 1, 2. Okay, so if I sketch these, I'm going to go from 0 to 4. So if I plug these into the y equals equation here, I'm going to get, when I plug in x equals 0, I get negative 2. When I plug in x equals 1, I get negative 1. 2, I get 0. 3, I get 1. 4, I get 2. I'm going to sketch this as a red graph. So 0 and negative 2, 1 and negative 1, 2 and 0, 3 and 1, 4 and 2. So that is actually the line x equals y plus 2, just so we know. Oops. My goodness. Okay. Then I'm going to sketch the x equals y squared 1. Don't know what I just did. Y plus 2. Okay. In blue. So when I go to sketch this one from 0 to 4, when I plug 0 into this, because that's the easiest way to get the equation, 0 in for x, I get 0. When I plug 1 in for x, I get plus or minus 1. When I plug 2 in, I get a decimal, so I'm not going to do these, but you can plug them in. When I plug 4 in, I'm going to get plus or minus 2. So I picked easy ones to do. Now 2 has a decimal and 3 has a decimal. I just don't feel like dealing with that. So at 0, I'm at 0. 1, I'm at 1. Negative 1, I'm at negative 1. And then 4, I'm at 2. And then I'm at negative 2. So this is the x equals y squared. And I want the region that's bounded between the two. And I didn't give the y values where it's bounded. So I'm going to have to find those. So I want this. So if you look, the red one is actually further to the right. And we are going with them to the y, not the x this time. So we're saying how far the furthest one to the right from the y, because these are y equals equations. So the red one is the further one. So when I go to draw these out, I'm going to say x. Ooh, I am still on highlighter. X equals y plus 2 is greater than x equals y squared. But now I need the a and the b. Well, the a and the b now are on y's, not on x's, right? So my one intersection for y is at -1, and my other intersection for y is at 2, because we're doing this with the y's, not the x's. So it would be y equals, sorry, not y equals, horizontal lines are x equals -1 and x equals 2. And those would be my a's and my b's. Now, remember in step 2 I had to find out where they intersected? I only found out where they intersected by using the graph, but I can use the equations to make them intersect. So I can set the x equals equations equal to each other, because I have x equals y plus 2, and I have x equals y squared. Now, if x equals this and x equals this, I can say x equals x, right? So that's why I can say y plus 2 must equal y squared. Now I have a y squared, so I want to get everything to one side. So I'm going to go 0 equals y squared. I'm going to subtract my y, and I'm going to subtract my 2 by moving these over to this side. And then I'm going to say what multiplies give me -2 and adds give me -1. So I'm going to get y minus 2, y plus 1. And so I get y equals 2 and -1, which I found by looking at the actual graph. But I could have just used algebra to find them. And then I just do the same integral deal. So I'm going to do an integral from, that's my a, that's my b, so -1 to 2. And then I'm going to go y plus 2, because it's the furthest on the right, furthest to the right, y plus 2 minus y squared dx. And so then I'm going to do -1 to 2, y plus 2 minus y squared dx. And then I do the antiderivative of that. And it doesn't matter if they're x's or y's, you do the integral the exact same. So now I'm going to get y squared divided by 2. So I'm going to put a half in front instead. Plus 2 is a constant, so it would have been 2y, minus y cubed, but I'm going to divide by 3, so 1/3, plus c, from -1 to 2. Then I get to plug them in. So I get 1/2 2 squared plus 2 times 2 minus 1/3 2 cubed plus c minus 1/2 -1 squared plus 2 times -1 minus 1/3 times -1 cubed plus c. These are going to cancel. Back to my black. So I'm going to get 2 plus 4 minus 8/3 minus 1/2 minus the minus 2, so plus 2, and then minus 1/3. And so I get 4.5 square meters. You only have one lesson left after this for the next 2 weeks. It's going to be Volumes of Revolution. It's just a really beefy one. So that's it for area between curves. I've given you an example of all the types that you will be able to see in your assignment. So you should be able to at least look at one of these past examples to help you out. Hope you have a wonderful week. And once again, I miss you guys, as you know, and this has been a very, very, very long time being away from you guys. But I hope you're finding the positives and finding good things to do and make this be a good time rather than a sad time. I love you all. See you later.